Welcome back to Dave Does Math from Home. We are now getting into part 2 of our videos on dot products. In the last video, we had established that dot products are a metric of the same directionness of two vectors that sometimes gets muddled up by the magnitude of those vectors. Two vectors that point in the same direction but are bigger will give you bigger dot products than those same two vectors that are smaller. So the magnitude of the vectors contributes to a dot product, but if you use unit vectors exclusively, you take away the influence that the magnitude has, and you're left with just a way to measure same directionness for two vectors. So I want to explore that idea a little bit more, because this isn't the first class in which I've used the words same directionness, and I want to connect this idea of same directionness of vectors with the last time I was talking about same directionness from pre-calculus. So I want to talk about sort of the range that dot products can give you. If we limit ourselves exclusively to unit vectors, the question I want to ask now is, what is the biggest dot product you can get from two unit vectors? So, if dot products measure same directionness, stands to reason that the biggest possible outcome you could get would be from two vectors that are pointing in exactly the same direction. And if you have two vectors that are pointed in exactly the same direction, and they're both unit vectors, that means that they have the same direction and the same magnitude, and it basically means that they're the same vector. So we can figure this out. We can answer this question just by picking any unit vector and multiplying it by itself to see what kind of dot product we get from that. So from a couple videos ago, we had a unit v vector that we said was 3/5, 4/5. If you're unclear about why this is a unit vector, pause the video and check. You can find the magnitude of this pretty easily. So verify that if you like. I'm going to trust that it is a unit vector because I recorded the other video like 20 minutes ago and I just remembered. So this is a unit vector. I want to find what happens when we take the dot product of this unit vector with itself. So that would be 3/5 times 3/5 is 9/25. 4/5 times 4/5 is 16/25. If you add those together, you should get 25/25, which is 1. So, the biggest dot product we can possibly get from two unit vectors is 1. This is the max. And this means that your two vectors are pointed in the exact same direction. There is zero difference between those. Zero difference. So, the next question I'm going to ask, hopefully, is pretty obvious, and that is, what's the smallest dot product you can get from two unit vectors? So to answer this one, we're going to use similar reasoning. We answered this one by figuring that the biggest dot product you could get was from two vectors that pointed in the exact same direction. So the smallest dot product you can possibly get is from two vectors that point in the exact opposite direction. So I'm going to go back to unit v, which is 3/5, 4/5. And I'm going to multiply this by unit u, which we'll say is negative 3/5, negative 4/5. You can always find a vector that points in the exact opposite direction of something just by making it negative. You're essentially multiplying it by negative 1. Negative 1 will completely change the direction to the opposite direction. So this dot product, unit v times unit u, should give me negative 9/25, not comma, plus negative 16/25, which is negative 25/25, which is negative 1. This is the smallest possible dot product you can get from two vectors, from two unit vectors. So negative 1 is the minimum, and that implies the exact opposite direction, which, if we're talking about exact opposite direction in degrees, this would be a 180-degree difference. So we have the maximum possible output from two unit vectors being 1, representing 0 degrees of difference, and we have the minimum possible dot product of two unit vectors being negative 1, which corresponds to a 180-degree difference. The middleist dot product you can get in between 1 and negative 1, hopefully we can agree that that should be 0. And a dot product of 0 implies that two angles are perpendicular, which is a 90-degree difference. So the question now becomes, what idea can connect these dot products? A maximum of 1 that corresponds to 0, a minimum of negative 1 that corresponds to 180 degrees, and something that middles right at 0, which corresponds to 90 degrees. What idea connects this? 90 degrees to 0, 180 degrees, negative 1, 0 degrees, positive 1. There is an idea that connects these things perfectly, and it's an idea that you have experienced before and worked with for a long time. I'm kind of talking around it because I want you to think about it, and I'll tell you in a second when I'm done talking around it, but you'll have to wait. If you've already guessed it, then I'm very proud. If you haven't already guessed it, it's the cosine. Cosine of 90 degrees is 0, cosine of 180 degrees is negative 1, and cosine of 0 degrees is 1. The other context in which I have mentioned same directionness is as angles. My personal definition of what an angle is and what an angle measures is that an angle measures the same directionness of two lines. And angles measure that same directionness on a scale, I mean, give or take coterminal things. The scale for same directionness of angles is 0 to 180. The scale of same directionness on dot products of unit vectors is negative 1 to 1, and the idea that connects those is the cosine. Which gives us this really, really cool formula. If you ever need to know what the angle between two vectors is, you can find it because the cosine of that angle is the dot product of the unit vectors. Here I'm expressing the unit vectors as the vector divided by its own magnitude. This is that vector divided by its own magnitude. So each of these is a unit vector, and the dot product of that unit vector is the cosine of the angle between them. Another way this commonly gets written is that theta equals the arc cosine of unit u dot unit v. So that's what dot products mean. This is what they're used for. They do get used in this context a lot to determine the angles between two vectors. Mostly we're going to use them to sort of measure same directionness between things. And we're going to keep in mind that when you have a dot product of 0, that means the two things are perpendicular. If you have a dot product of 1, that means that their unit vectors point in the same direction. Dot product of -1 is opposite directions. And so you can sort of gauge the in-betweens. If you get a dot product of 1/2, well, if you get a dot product of 1/2, you know that it points in exactly, is that 60 degrees? Cosine, yeah, cosine of 60 degrees is 1/2. So 1/2 is 60 degrees, root 3 over 2-ish is, what is that, 0.7 would be root 2 over 2. So if your cosine, or if your dot product is 0.7-ish, that's about a 45-degree angle. If your dot product is 0.86-ish, I think that's the root 3 over 2, and you have about a 30-degree angle. So you can kind of eyeball the angles between things using dot products. It's very nice. The really cool thing about this is that I've done all of this in 2 dimensions, because that's what I can draw and like communicate in. But this works in 3 dimensions as well. So you can take the dot product of 2 3-dimensional vectors and get the angle between them. Because any 2 of those angles, any 2 vectors lie on a plane. And so whatever that plane is, the angle between those 2 vectors on that plane, you can find using the arc cosine of a dot product. It's pretty powerful mathematics. It gets used in a lot of things. I think you might see there's some problems somewhere in the homework. They deal with various angles of elevation and angles of trajectories and things. It's pretty interesting stuff. That is about all that I have to say about it. So I hope that this has given you a better and more thorough understanding of dot products. And I'll see you in the next one. Next one's cross products. Those get weird.